Hello and welcome to the lens maker's formula and how to solve problems related to that. So now we know that the lens maker formula is used to make a lens. So here it is, right? So we have a lens which is convex lens. The radius is R1 and R2 and it is immersed in a medium N1 and the refractive index of the lens is N2. And we know that the focal length for this lens is given by 1 by f is equal to N2 by N1 minus 1 into 1 by R1 minus 1 by R2, and we just have to use the proper sign convention to get the focal length of this particular lens. And if you want to create a lens for a particular focal length, we can manage R1 and R2 and also the refractive index to make a lens of particular focal length. Now here is an important point. We want to just see that how the focal length of a lens varies on which all things, right? The first thing is first the focal length of the lens varies, depends upon the refractive index of the lens itself. Secondly, the medium in which the lens is, and also on the R1 and R2, right? So depending upon R1 and R2 and their signs, right? So their geometrical shapes. Is it a convex or a concave, right? So R1 and R2 can change accordingly with the sign convention. If you haven't watched our video for the lens maker formula, please watch that first before we move to the problem solutions, right? So with that, basically we'll try and solve few problems and it is very easy. You can find the focal length if we can give you like N1, N2, R1, R2 and things like that. But what we want to dive is by solving few IIT problem and how the problem can be solved and how it can become complex, right? So let's start with our first problem. So it says that we have a concave and a convex lens is made of a glass with refractive index 1.6 has a focal length 10 centimeters. Find the focal length of the lens when it is immersed in a liquid with refractive index 1.5 and 1.7 respectively, right? So we have a concave surface, then we have a convex surface, we have a lens like that, right? We have a refractive index N2 which is given 1.6 and it is in the first case it is in the air, so N1 is 1, right? Now it is a focal length of 10 centimeter. It is also given, so we can find looking at the formula, right? So let's write down the formula first, right? So 1 by f is equal to N2 by N1 minus 1 into 1 by R1 minus 1 by R2, right? This is given to be 10 centimeters. N2 is given, N1 is 1 and this is unknown, right? Now we can use that unknown part and we can find this unknown part pretty easily using these numbers, right? So let's find that out. And that we need to immerse the lens, so which means we are going to change N1, right? But this will remain same because we are not changing the geometry of the lens, right? And we can use that to find the focal length. That should be our strategy, right? So let's try and solve that, right? So 1 by f in this case is 1 by 10 centimeters and N2 is 1.6 and it is in the air minus 1 and 1 by R1. Now let's look at the sign first, right? It's a concave or convex. So ray of light is going in this direction, so this is positive sign, this is negative sign, right? So R1 is actually minus R1, it is falling on this side, and the R2 is again negative, so R2 is minus R2 and we are going to put that over is minus R1 and this will become plus R2, right? So 1 by 10 is equal to 1.6 minus 1 divided by 1, which is 0.6 into 1 by R2 minus 1 by R1, and we don't know the R1 R2, so we'll just keep that because we just have to find the ratio when the n changes, right? So let's try and find the value for this expression over here, which is 1 by R2 minus 1 by R1, and that is going to be equal to 0.6 0.6 will go down, right? And sorry, so we have 0.6 into 10, so it will be 0.1 divided by 0.6, right? We'll keep that expression for now, and let's plug that in for the different things we want to calculate. So now the lens is immersed in a medium, which means that the n1 is going to change, right? So n2 remains the same because we are not changing the lens itself, and r1 r2 remains the same, and we need to find the new focal length, which is going to be, let's call that 1 by f2, right? And then the refractiveness of medium is same, which is 1.6, and now it is in a medium which has a refractive index 1.5, right? So we divide that and we call it n1 is now going to be 1.5 minus 1 into 1 by r2 minus 1 by r1, right? This value is known, so 1 by f2 is going to be 1.6 minus 1.5 divided by 1.5, right? And this value is now known, is 0.1 divided by 0.6, and this is going to be equal to 0.1 divided by 1.5 into 0.1 divided by 0.6. Okay, and when you solve that, basically it's 15 into 6 divided by 1 into 1, and that is going to be equal to 90 centimeters. Okay, so the f2, the 1 by f, right? F is going to be 90 centimeters. This is our f2. You reverse that, right? So f2 is going to be 90 centimeters where it is immersed in a liquid with 1.5 refractive index 1.5. What it means is that there's a lot of difference, right? So this lens was here, right? It has a focal length of 10 centimeters. Okay, now we immerse that in a liquid with refractive index 1.5, and suddenly its focal length changes 9 times, right? From 10 centimeters all the way to 90 centimeters. So definitely the medium in which the lens is, there is a lot of effect, right? So now let's see if the medium in which the lens is greater than the refractive index of the lens itself, right? Now let's look at the formula again. So 1 by f is equal to n2 minus n2 by n1 minus 1, 1 by r1 minus 1 by r2, right? So when we sort of immerse a lens into a medium n1, right? Generally it is air, right? N1 is equal to air. But so when we immersed a lens into a medium with refractive index n1, what is going to change? This one is going to be same, this will change, r1 will be same and r2 will be same, and the impact of this change is very huge, right? We have seen in this example that the focal length actually changed from 10 centimeters to 90 centimeters. Okay, now here is a case where n1 is actually greater than n2, which means the lens has a focal length, the refractive index of the lens n2 is 1.6. Now it has changed, so n1 is now 1.7 in the second case, right? Then what happens? Now this one is going to remain same. Okay, so that is not an issue. Let's look at this one, n2 by n1 minus 1, right? What is going to happen if n1 is greater than n2? So this will become n2 minus n1 by n1, and because n1 is greater than n2, this number is going to be less than 0, which means that focal length will become negative. What it means is simply that now this convex lens, because of the shape, right? So we had this shape. The shape is defined by, in this lens maker formula, right? It's n2 by n1 minus 1, and this is 1 by r1 minus 1 by r2. This part defines the shape of the lens, right? So we had this convex lens. Okay, now this defines in the medium we are, now it is become negative. Now this part is positive multiplied by a negative part, hence the focal length becomes less than 0 or negative, which means that this convex lens, which is acting as a converging lens, when immersed in a medium, right, in that case, immersed in a medium which is more than the index of refraction itself for the lens, this will start acting as a diverging lens. So instead of converging the lens, converging the rays, it will start diverging that, right? So that is amazing. So remember that the shape of the lens does not matter, right? In the medium in the which the lens is also matters. Okay, so with that, let's try and find out the new focal length for the lens, where when we have this n1 in the medium which is in 1.7, and the refractive index of the lens is 1.6, and everything else remains the same. So we are going to call it 1 by f2, and now n2 is 1.6 divided by 1.7 minus 1, and we already have a value of this one, right, because we're negatives. So now we know that, and that is, so 1.6 minus 1.7 divided by 1.7, and this value we have already established that, and that is 0.1 by 0.6. So we are going to put that over here, and that is going to be equal to minus 0.1 divided by 1.7 into 0.6, that is 1 by f2. So the f2 is going to be equal to 1.7 into 0.6 divided by point into 0.1 with a minus sign, and when you solve that, basically we'll get minus 1.2 centimeters. Okay, so now a converging lens or a biconvex lens which looks in a shape like that, when immersed in a medium, right, is going to act as a diverging lens, right? So shape does not matter. There is a huge impact of the relative refractive index of lens and the medium it is in. Okay, so n1 and n2, very important, right? Both of them very important, and their relationship will define if the lens is going to be converging. So in this case you have n2 and n1, where n2 is greater than n1, and if it is other way around, the shape will remain the same, right? But now it will become a diverging lens, right? So this is n2, this is n1, now n1 is greater than n2. So as you have seen, the initial focal length of the lens was 10 centimeters, right? So let's sum that up. So the initial focal length, here was our lens. In the air, the focal length was 10 centimeters. Okay. And then when we immersed in a particular liquid, not slightly higher, but just very little higher. So it was 1.5, and immersed, sorry, the refractive index was 1.6. We immersed it in liquid with refractive index 1.5, right? The focal length increased a lot, became 90 centimeters, and we do other way around, right? So we have this 1.6 now immersed in a liquid 1.7, right? Starts acting as a diverging lens, and the focal lengths become negative, and in this direction changes from 10 centimeter positive, right, to minus 102 centimeters. So there's a huge change in the focal length. So be careful when you're solving and using a lens maker formula. There's a huge impact of n1 and n2 on the solution, and that's what we want to highlight using this problem. And this concept will be checked many times when you encounter problems like that, and this is one of the favorites for the exam. Now let's look at another problem which says that what is the relationship between refractive index mu1 and mu2 if the behavior of the light is shown below, right? Now here is the refractive index of lens is mu, and it is immersed in a medium mu1, and the ray of light is passing without deviation. Okay, in the second case you have a refractive index of the lens mu, and the ray of light is passing, not converging but diverging, though the shape is convex, right? So definitely if there is no change, there is no change in the direction, which means that the mu has to be equal to mu1. Okay, hence there is no change. Now here, because of the shape is convex, but the behavior is concave, right? Which means that the mu2 is greater than mu. Okay, so what is going to be the relationship between mu1 and mu2? So mu2 is greater than mu, and mu is equal to mu1, so mu2 is also going to be greater than mu1, and that should be our answer. So very simply, you can find relationship between this refractive index if you just pay attention to the lens maker formula and how the refractive index of the lens and its condition to the in the environment which it matters a lot, right? So now let's look at another problem from JEE 2010, right? So two transparent medium of refraction is mu1 and mu3. So mu1 and mu3 have solid lens shape transparent medium of refraction is mu2. So there's a lens in between the medium mu1 and mu3 as shown in the figure. The ray traversing this medium is also shown in the figure. So in the column 1, different relationship between mu1, mu2 and mu3 given. Match them to the ray diagram shown below, which means you have to find where this condition is met, this condition is met, and this condition is met, right? So now we have to simply go to the fundamentals where we say here is a lens or a medium, right? So this is refractive surface 1, and what is the behavior of light on this refractive surface 1? Okay, and what is the behavior of light on this refracting surface 2, and accordingly decide that what is the refractive index or relationship between this refractive index over here. Okay, so let's look at a simple one. Let's say when the mu2 is mu3. Okay, if the mu2 is mu3, then the no refraction will happen over here, right? Depending, doesn't matter what the shape is, right? The ray of light is going to pass straight. Okay, if the refractive index is same. So let's see on this interface between mu2 and mu3 where the ray of light is passing straight. Look over here, right? The ray of light is coming like this, getting refracted, and now it's passing straight, right? So mu2 is equal to mu3 is this one. Okay, and here the ray of light is coming, getting deviated, no required. Here the ray of light is coming, now it is passing straight between mu2 and mu3 interface. This is also the case. Here it is coming on this interface, it is getting deviated, so this is not true. In here it is coming and passing straight, right? So this is also true, which means that for this one options are P, R and T. Okay, now let's look at, sorry, before it becomes like too complex, I'll just write it down for you. So P, R and T. Okay, for this one. Now, so there is no equal sign. Now we have to sort of go back to the fundamental when we said here is a refracting surface, right? Any surface, and the ray of light is coming like this, right? So let's say it has a refractive index mu1 and mu2, and if mu2 is greater than mu1, right? If the mu2 is greater than mu1, what is going to happen? The ray of light is going to bend towards the normal. So this R and I, in this case, R is always going to be greater than I, right? That's a fundamental Snell's law which suggests how the refraction has to behave, right? So here is the case where we are going to say the refractive index of the lens, right? So let's look at this example, right? Where now we are going to say the mu2 is greater than mu1, right? So here the mu2 is going to be greater than mu1, which means the ray of light has to bend towards the normal. Okay, so now which are the cases where the ray of light is bending towards normal? So here is the surface. Okay, the ray of light is coming like this and bending like this. So we are only interested in this surface right now, right? So here is the normal you have to draw from the center. Okay, so let's draw the normal from the center. The ray of light was going like that, right? So instead of going like that, it bended like that. Okay, so definitely here the mu2 is greater than mu1, right? So this is the case, Now look here, a ray of light was coming like this, right? And here is a normal, it's coming like this, right? Bends away from the normal. In this case, look over just over here, right? It's bending away from the normal. So this is not valid one. Now let's look here. The ray of light is coming like this, then goes like that. Now here is the normal on this side, right? In this surface, right? This is a normal. The ray of light is bending towards the normal. Okay, so this is also true for this one. Now look here, on this surface, the normal is like that. The ray of light is going bending away from the normal, so this is not true. And over here, this is a normal. The ray of light is coming like that, bending away from the normal, right? So mu2 is less than mu1, but here we want mu2 greater than. So this is the only two cases, and we are going to write that. And the answer for the first case is P and R. Okay. So just by following Snell's law fundamentals, you can solve these problems. Let's try the other way around when the mu1 is greater than mu2. Of course, we said P and R is not there, so we are going to eliminate that. And look here. So on this interface, we have Q, right? So it's bending away from normal, right? Other way around. Sorry, this is this other way around. So for this is true. Again, as expected, this is true. And also here, right? Here is normal away. This is also true. So for this number 2 option, we've already found R, and this one is going to be our Q, S, and T. And now on the second interface, we'll to find out when the mu2 is greater than mu3, right? So this is a mu2 and going to be mu3. So if a reflection is happening like this, mu2, mu3, right? The ray of light is coming, and we know that the mu2 has to be greater than mu3, which means that the ray of light has to bend away from the normal. If so, whatever is that case is, this is going to be true, right? So when the mu2 is greater than mu3, right? So mu3 is a lateral medium. So with that, let's look at all of them in here. Now the ray of light on this interface is passing straight, right? So that is out of question. Okay. Now let's look at this one. So here is normal. The ray of light was supposed to go straight in this direction, but bend away from the normal, right? That's what we want. So this one, and then over here it is passing straight, out of question. Now this one here is the normal, it's going away, so that's true, right? And now over here again passing straight, so that isn't true. So finally, sorry, I have marked the wrong arrows, right? So this is the last one we are looking at. Okay, so finally this one is going to be equal to Q and S. Okay, this is Q and S, and that's how we solve the problem. So always remember, whether it's a lens or any spherical surface or any kind of a straight surface, right? The Snell's law will be always be valid, right? And this question tries to check that, do you really know the Snell's law, and can you fundamentally apply that, which says that if a ray of light is coming like this, right? And here is a medium 2, here is a medium 1, and the refractive index of medium N2 is greater than N1, the ray of light will bend towards the normal, right? So this angle is always going to be small. In the other case, if the refractive index is here N1 and N2 and ray of light is coming like this, right? And if N1 is bigger than N2, the reverse case, right? So N1 is bigger than N2, so the ray of light is going to bend away from the normal. This angle will be bigger in that case, right? So with that, we can solve that problem pretty easy if you know the fundamentals, and can score a few marks solving that. So let's move to the next one, right? Now we have a thin convex lens made of a crown glass with mu is given to be 3/2, right? So we have a thin convex lens made of ground glass with mu 3 by 2 has a focal length f. So we know the focal length f, right? So in the lens maker formula, we know one variable, we know two variables, and it is probably in air. So we know f, we know n2, and we know n1 as well. What we don't know is the r. So let's see. So when it is measured in two different liquids having refractive index so and so forth, has a focal length f1 and f2 respectively, and we just have to find the relationship between that, right? So the same problem we did, right? So the lens maker formula 1 by f is equal to n2 by n1 minus 1, going to be 1 minus r1 by 1 minus r2, right? We know this, for the case 1, we know this, right? And we don't know that, right? And we know that if we are going to immerse the lens, right? So this is a lens, right? We are going to immerse in certain liquid. This one is not going to change, and this one we can find out from the first case, and we can use that for the case number 1 and 2, which is given for the f1 and f2, right? So let's do that. Very simple. Here let's apply the formula. So 1 by f in this case, we can find that, right? So first let's always draw the our sign convention here. So here's the ray of light coming, this side is positive and this side is negative. Now r1, right, is going to be on this side, so r1 is positive, and r2 is going to fall on this side, so r2 is negative. So with that we are going to put that number, and everything is a convex length, so f is positive. So with that we can put it over here. So 1 by f, we don't have a numerical value but we have f, okay, so we are going to put that f. So 1 by f is going to be n2, right, which is 3 by 2 divided by in the air minus 1, and now we have r1 we have already written as a positive, right? So 1 by r1, and r2 is negative, so 1 by minus r2, and that is going to be 3 by 2 minus 1 into 1 by r1 plus 1 by r2. And because it is a bioconvex lens, it is going to be same, but doesn't matter, right? So we know this is nothing but 0.5 into r1 plus 1 by r2. We just want to find the expression in the case where we want to calculate the other focal indices when we want to immerse the lens into different medium, right? So it is nothing but the f, this value, right? We are interested in 1 by r1 plus 1 by r2. It's going to be constant always. So 1 by 2 is going to be 2 by f. Okay, so 2 will go over there, and then we're going to log that. Okay, now let's find f1 when it is immersed in a refractive index 4 by 3. Okay, we're going to say now this is 1 by f1, and now the refractive index of the lens is not going to change, it is going to be the same, right? So it is going to be 3 by 2 minus 4 by 3. Okay, sorry, so let's write down the formula first. Okay, to clarify, 1 by f2 is equal to n2 minus n1 minus 1, and this is going to be 2 by f. We already know that, right, from here. So now we know the n2 is going to be the refractive index of the lens, that is not going to change, that is going to be 3 by 2. Okay, so I'll write that down, 3 by 2, and the n1 is the refractive index in which it is going to be immersed, and n1 is now going to be 4 by 3. It's quite cool. So going to be 4 into 3 minus 1, and that's going to be 2 by f. Okay, so that's 9 by 8 minus 1 2 by f. It's 9 minus 8 is equal to 1 by 8 into 2 by f. That's going to be 1 by f1. Okay, now let's look at what we have, options, things like that. So relationship between f1 and f, right? So here f1, right, is going to be f into 8 divided by 2, which is 4f. Okay, so f1 is going to be greater than f, right, 4 times, right? So do we have that over here? Yeah, so we have it here, right? F1 is greater than f1 and negative or not negative, f1 is equal to less than, this is untrue, right, because f1 is greater than f, right? Now let's look at f2 and then we'll be able to find our answer. So f2 is also very simple. Now we're going to write the lens maker formula with the same thing, right? So we have this 1 by f2, now the refractive index of the glass, 3 by 2, that is divided by 5 by 3 minus 1, and we already have that expression for 1 minus r1 by r2, which we can simply use, which is 2 by f. Okay, this is 2 by f, and now here the expression will become negative, right? So we have 3 by 5, sorry, 3 by 2 into 5 into 3 minus 1, 2 by f, 9 by 10 minus 1, 2 by f, that's going to be minus 1 by 10 to 2 by f, right? So the f2 here is going to be less than 0, right? For a simple reason, because this number is bigger than this number, right? So now we have this n1 which is bigger than the refractive index of the lens, so that is going to be negative, and right now we have that, so f2 becomes negative, that is true. And here f2 is greater than f, that we need to figure out if that is also true. And here we have, let's find out for the f2. f2 is going to be minus 5f. Okay, so it is negative, it's not going to be greater, it's going to be negative. Sorry, f1 becomes negative, so that's not true, that's positive. f1 and f2 both becomes negative, that's also not true. So here is the answer, which is option number B, right? So simply using the lens maker formula, plugging in the right numbers, you can solve problems like that. So now let's look at other one. Now two glasses with refractive index 1.5 and 1.7 are fused to make two identical convex lenses. Find the ratio of focal length. How will each lens act when a parallel ray of light incident on a lens when they are submerged into liquid? Okay, so now what we are going to do is that basically we have two glasses, right, and we are going to make lens number 1, which has a refractive index 1.5, and the other one which is a refractive index 1.7, right? Now we have to just first find the focal length, the ratio of focal length. So let's call the focal length f1 and f2. Now how do we find a focal length? Simply using the lens maker formula, which is that n2 by n1 minus 1 is going to be 1 by r1 minus 1 by r2, right? And we just have to find the ratio of f1 and f2, which means this is going to cancel, right? So all we care is about n2 minus n1. N1 is also same in the air, right? So let's do that. So 1 by f1 is going to be 1.5 minus 1, it's going to be 1, right? And this expression, let's call it x. And now 1 by f2 is going to be 1.7 minus 1, and this expression will remain same, right, because the same glass, right? So this curvature will remain same. Let's take the ratio. So let's do that. So here 1 by f1 is going to be 0.5x, okay, and 1 by f2 is going to be 0.7x, and now we are going to divide that, and basically f1 by f2 is going to be 0.7 0.5 xx cut, that is 1.4. okay, So we have our first part, the ratio of the f1 and f2, and that's what we wanted to find out. Now, how will each length act when a parallel ray of light incident on the lenses when they are submerged into liquid with a refractive index 1.6? Okay, so just looking at, and we know the lens maker formula now, both the lenses are submerged into liquid with refractive index 1.6, right? Now this 1.6 is greater than 1.5, which means that this converging lens is now going to act like a diverging lens, right? And in here, the refractiveness of the lens is more than the medium, so it will keep on acting as a converging lens, though the focal length is going to increase, right? The focal length will increase as we've seen in the other problem. So with that, we conclude this. So let's move to the next problem. Now, a diagram below shows behavior of rays from point objects O. Okay, so this point object O. Now, biconvex lens. The lens is basically a thin glass enclosed which is filled with liquid of refractive 1.3. I think this should be biconcave. Okay. So this is going to be filled with a refractive index 1.33. Okay. Which diagram correctly shows the passage of light when the lens is in the air, right? So now the lens is in the air. So in that case, we always know F is going to be N2 by N1 minus 1, 1 minus R1 minus 1 by R2. And this is going to be, let's say, X. We are not worried about that. All what matters is N2 into N1. And we know that if the N1 is greater than N2, a converging lens will become a diverging one, and a diverging lens will become a converging one. And if n1 is equal to n2, there is no going to be change and they will be equal, right? So the ray of light will pass straight. So with that, let's start. So here we have the lens is in the air, right? So with that, we have a lens which is made up of 1.33, which is in air, so it's going to act like a normal diverging lens, right? The n1 is less than that, so here it is sort of diverging lens. So here is the answer for this one. Now the lens is in water, which is 4 by 3. The 4 by 3 is also 1.33. Yeah. So now, which means that the refractive index of the lens and the medium is same. So the ray of light is going to pass straight, right? Now in this case, it pass straight. So that is the solution for this one. Now the lens is immersed in a medium which is concentrated sugar with refractive index 1.5. So here's the lens 1.33 immersed in a medium 1.5, which means that N1 is going to be N2. Now it's a converging surface, it will start acting, a diverging surface will start acting convex lens. So the ray of light will come like this and will behave like a converging lens. So this is the solution for this problem. Now let's move to the other one. A focal length of a thin lens is a characteristic of a lens material. True or not true? So is a focal length, right? This is N2 by N1 minus 1 into 1 by R1 minus 1 by R2. See, I'm writing the lens maker formula so many times, right? And you will be able to see it depends upon the characteristic of the medium, right? Which is N2. The same on both sides of the lens irrespective of two medium in which it is placed. It is not that case, right? In the medium you are placed in, that is going to matter, right? So this is untrue. Depends upon the radius of curvature of the lens surface. Of course it does, right? So it is also true. Dependent on the medium in which the lens is immersed as well as on the geometry of the surface. So this is matter. And the geometry of the surface, meaning is it the convex side or convex side? No, it matters, right? None of the above options explain it completely. Now, here we are just saying it depends upon the characteristics of the lens, right? Actually depends on the radius of curvature in the medium as well, right? The same for the both sides, we have already cut that. Depends upon the radius of curvature of the lens surface, but it also depends upon the refractive index, medium like that. And so forth, we can refuse this, and basically the E is the correct answer, right? So we tried to solve a couple of problems here. I know I did it quite quickly today, but you remember the lens maker formula is very simple. You have to be very careful of this guy N1 over here, right? In the medium it is in, and that's what will change the focal length of the lens a lot. And you will get a question like this always in the exam. So this is a very important concept, and you can do many revision problems, right? Please do that. And if you want to watch more videos, you're welcome to go to Deep Dive Physics. And also subscribe to our channel. And if you go to Deep Dive Physics, you will have a very structured playlist which you can watch without any advertisement. And we also provide one-to-one study sessions and guidance. If you're interested in that, please get in touch, right? And we'll be happy to help.